Hey guys, so today we're going to go over last week's homework and quiz. There's exactly less than 2 weeks at this point left in the semester. We don't have a ton of material left. We're going to go over chi-squared, which is another type of inferential test for when both your variables are categorical. We'll go over that tomorrow, and then we'll move on to simple linear regression and multiple linear regression. So I hope you're making progress on your projects. Please reach out to me if you haven't to review that progress. So like I said, today we're going to go over last week's homework and quiz. We'll start with the homework. Most of you did really well. Just a few points of clarification I want to make. First, your alternative hypothesis is that at least one group mean is different than the others. And a lot of you had things that were similar to this, but subtly and significantly different. So it's not correct to say that, at least a pair of means are different, right? It could be as simple as just one. And then similarly, you shouldn't say one group mean is different, because you could have 2, 3, 4, 5, all the way up to J is the index we used for going through groups. Up to J means being different. They could all be different, in other words. So that's an important distinction that I want to make is your alternative hypothesis for an ANOVA should be that at least one mean is different. And further, if you don't want to write it that way, you could just write not H of O, because your null and your alternative should kind of complete the space of possibilities. So, not H sub O automatically completes the range of possibilities, whereas when you say at least one pair is different, you're excluding a lot of other scenarios that don't quite fit into the null, that they're all equal, or the alternative. And then secondly, a couple people skipped the EDA portion of the homework. I did not take points off because JUMP does some EDA when you run your test. But the EDA is really important because it gives you a quick sanity check as to what you expect the results of your inferential test to be. So please don't skip that moving forward, and definitely not in your projects. As I said, it's a good baseline. When you did your EDA, and many of you did do a great job on the EDA, you could see that the mean amount of home runs across divisions was roughly the same. So your p-value would then not be a surprise when it's greater than alpha. Lastly, for part 3, a lot of people wrote down that the t-test compares two groups, so an ANOVA is more appropriate. I know that in the homework we did, we used two groups. However, a t-test can compare a single group as well. So again, this is a subtle but important distinction. A t-test compares at most two groups. It's at most two groups. But in a comparison, you could compare a group to a constant. And we did examples like this during lecture where we looked at like the mean temperature of people who lived in Florida, right? We weren't comparing people who lived in Florida to the rest of the country. We were just comparing people who lived in Florida to a constant of what we expect the average temperature to be. So again, a subtle but important distinction. So moving on, we'll go over the quiz now. And this is the data you were given, 3 brands of chicken feed. I'm going to make this a little bigger so it's easier to read. Right, and it looks like 3 chickens were put on each diet. So in this case, both I and J are, within group, there's 3 chickens on each feed, and there's 3 types of feed. So let's start with computing the mean of everything, because that's going to be helpful in 2 of the sum of squares. So we just do average. Now we have our means. Oops. Okay. Let me make this all bigger. Okay. And we don't need so many decimals, so I'll make it a little simpler. Maybe 3 decimal places is plenty. Okay, so now let's start by, and it's up to you what you want to do first. I like to start with error. You could do sum of squares total as well, is another easy one. And I did not compute the overall mean, so let me do that as well, because that's going to be important for sum of squares total and sum of squares group. So this is our overall mean. And let's start with error, because that's the way we did it in lecture. So the error is going to be each individual observation minus that observation's group mean. And I'm going to sticky the row. Oops. Shoot. I used the alt key instead of the function key when I stickied, so we'll do that correctly now. Let me just grab the data. Okay, so here's our data. Make this bigger. Not too many decimals. Well, there's no decimals right now, so. Okay, we'll do the means again. So average. So here are our group means. And our overall mean is going to be just every data point with no regard to group. I'll label that too to avoid confusion. And now let's go ahead and compute all our errors. So we're going to take each data point, because that's like the actual, and then if we want the error, we want the prediction. So that's going to be the group mean, and this time I'll sticky it correctly. We want it to be stuck on row 5. Go across 3, across 3 again. These are our errors, but you might remember we actually want the errors squared. So let's square them. Okay, that gets rid of all the negative signs, which is a good sanity check. So now we have all our errors. To get our SS error, and I'm going to label this like this, error, and then group on top. Just because when you do your F statistic, error goes in the denominator, and total. We're going to do sum of squares here, degrees of freedom here. This is the traditional way ANOVA's split up. So for error, all we're going to do is sum all of these. And we got our error, which seems a little smaller than I remember, but we'll sanity check at the end if our results make sense. Sum of squares total, on the other hand, I am doing every data point, but this is much easier. I'm doing every data point minus the overall mean. So I'm going to double sticky it. And I gave you this. The reason I gave it to you is it makes it really easy to calculate sum of squares groups. However, if I were you, I would still calculate it myself. The reason being that it's a good sanity check that your work is correct. It's not even really a sanity check, it's a true check that you did everything correctly if you get if the sum of squares groups and sum of squares error sum up to sum of squares total. So let's do sum of squares group as well. And there's a common mistake that I saw a few people make here, but it's the group mean, right, minus the overall mean. We'll sticky that, and you square it. And you square it. But the trick here is, remember, these all have a double summation over I and j. However, we're not going over I here. We're only going over j. So you can't stop at this step. You have to account for that second summation. And the way you do that is you simply multiply it by your I index. How many times are you looping through I? And in this case, it's 3 times. So all of these should actually be multiplied by 3. And now we can do our check to make sure this is correct. And we sum them all up. And it looks like we might have done this right. It sums up to 1500.88 repeating. I'm just looking down here to see that. And we get 1501, which is, for all, it's off by 1/9, which is a little bit unexpected. It could be a rounding error, but let's round this out a little more and see if we can get more clarity on where that rounding error is coming from. So it's summing those, so that's right, it's summing those. Okay. Oh, and there we go. It was just here that we weren't showing enough decimal places, but they do sum correctly. Okay, and then the degrees of freedom here is kind of trivial because I gave you both the same number of groups and the same number of observations within each group. But for practice, let's be clear about what we mean. How many groups are there? There's 3. There are these brands of chicken feed. And don't forget you have to subtract 1 from the number of groups, so we get 2 there. And then how many observations are there within? Well, your error is actually more complicated than that, right? Because it's your actual minus your predicted. So your actual is your total number of observations, which we know to be 9. And then your predicted is kind of like your number of groups. So that's how many predicted values you have. So you have 9 minus the 3 predicted values gives you 6. And then remember, your total is really easy. It's your total number of values minus 1, which is 8. And you can sanity check that as well. And they do add up. So lastly, to calculate our F statistic, all we're going to do is take our sum of squares for group divided by its degrees of freedom, and then divide that by our sum of squares of error divided by its degrees of freedom. Now, how do you convert this to a p-value? It does depend on the statistical software, and in the chi-square example we're going to do tomorrow, I use R, but I'm going to show you how to do this one in Excel. If you just type in F, because remember, ANOVA is a type of F distribution, so the statistic you get, or a type of F test, so the statistic you get at the end does follow the F distribution. So we're going to do F distribution, and notice there's 2 choices here. We do want the right tail, because we want data more as or more extreme than what we observe. So we're going to do .RT for the right tail. And then this is our statistic, and you have to supply the degrees of freedom, because as you've seen, the shape of the distribution depends on the degrees of freedom, right? And we get a p-value of 0.713, which is not correct because I remembered it being significant. So we made a mistake here, and I'm guessing it's an order of operations issue. So let's see if I put these in parentheses, if that changes anything. Yep, there we go. So when you're calculating your F statistic, division isn't commutative the way multiplication and addition are. This is going back to algebra class. So just make sure you use parentheses appropriately. Because without the parentheses, what it's doing is it's taking the sum of squares groups, dividing by its degrees of freedom, then dividing by the sum of squares error, then dividing by its degrees of freedom. But really what you want to do is divide by this quantity, the sum of squares error divided by its degrees of freedom. And that gives you the right F statistic. So it was an issue of order of operations. So it's really easy to make a mistake here, and that's why it's really important to do these sanity checks. Like EDA here shows me these means are different. Like I can clearly see that these means are different than what we would expect. Actually, I think this is a typo. Is this supposed to be an 8 here? Let me just check the quiz real quick. It was supposed to be an 8. But yeah, I can clearly see, like, at the very least, Scratch and Peck is very different than Kalmbach and Purina. So, yeah. Good work on the homework and quiz. In our next lecture, like I said, we'll go over chi-squared, which I think is a very straightforward compared to T and F tests. Inferential test that also involves converting your data into a table. I'm looking forward to going through that with you guys tomorrow.